Okay, I'm going to get started. Good morning, everyone. Well, it's good morning for me on the East Coast here in Montreal. My name is Gary Scavone. I'm in the music technology group here at the Schulich School of Music at McGill University, and I am your chair for this morning's session, Stream B, just to make sure you're in the right session. This is Stream B, Capturing Performance. We have three different presentations this morning. One motion capture related to woodwinds, then a paper regarding trumpet players, and another on voice. And I'm still looking for the presenter for the second paper, but we have a little time in between sessions. So I don't want to delay things any longer. I'm going to turn it over to Laura Stambaugh at Georgia Southern University with a presentation on a motion capture study of the development of woodwind motor skills.
Good morning. Well, it's morning for me. I'm in the same time zone as Gary, and driving in this morning, saw a beautiful sunrise, so that was really nice for me here. And I know at least one of you, I don't even think the sun has come up for you yet. So thank you for being here if it's really early. Oop, here we go. So I'm interested in woodwinds because primarily I'm a woodwind player. And coming from the pedagogy of woodwind, when you learn to play a woodwind instrument, they tell you to keep your fingers really close to the keys, don't move them really far off the keys. But when people have started looking at what advanced woodwind players actually do, they actually move their fingers quite far away from the keys. And the faster they're playing, the higher they're lifting their fingers. So that disconnect between pedagogy and what's actually happening is something that caught my attention. There's a fair amount of motion capture studies looking at experts on pianos and string instruments. How are they moving various parts of their body? Where are the points of acceleration in their fingers? How does that relate to evenness and accuracy in playing? And then there's many fewer studies on woodwind instruments. There are no studies on beginners. So that's what I'm interested in. And the purpose of this exploratory study was to explore how right-hand fingers move during the earliest stages of learning to play a woodwind instrument using motion capture and digital performance technologies. My research questions were focused on evenness. So how evenly are people playing? How does tempo affect evenness? What type of pitch errors do they make? What are any trends, or how do their fingers move in terms of velocity? And then potentially to look at the motion paths of individual fingers. My participants were convenience sample, and they came from two different populations. Some of them were undergraduate students at a university, and my senior people came from a community band. So I had both novices and people that I'm calling experienced, because these were either an undergraduate music major or people who had been playing in a community band for 40 years, 50 years, a good part of their life, but they were not professionals. The focus of the data I'm going to talk about today will be with the novices, people who didn't play woodwind instrument until they walked into their first study session with me. But I will provide a little bit of comparison data for the experienced players. I had them playing on a Yamaha MIDI wind controller. And if you're familiar with wind controllers, there's a couple different types on the market. I chose this one because it has keys that you actually press down. There are some others where you just kind of touch the sensor, but here we do have keys. And the setup is very much like a soprano saxophone. I'm focused on the right-hand fingers, so F, E, D, C. And I'll refer to them as the first finger or index finger as finger number 1. The test tasks that I used, I was interested in stepwise motion. So they just have a simple scale pattern, and then thirds. So they're lifting 2 fingers, say from C to E, putting down 1 finger, lifting 2 fingers, putting down 1 finger. because the potential for coordination issues, of course, is going to be greater when you're lifting 2 fingers. And then the motion capture equipment was an Optitrack Certus. I had 2 of these 3-camera panels set up at about 90-degree angles. And my resolution rate was 200 frames per second. So participants came in for individual study sessions. First, I took some demographic information. Next, they did the digit span forward to assess for working memory. Then the 9-hole peg test. So in the United States, there's this game that they put out at family-style restaurants that has little pegs in it, and you have to move the pegs around the board or try to move them from one area to another. And the 9-hole peg test is sort of like that. You pick up tiny little pegs and you have to move them from one place to another as quickly as possible. And you do that with your dominant hand and your non-dominant hand, and it's a measure of finger dexterity. Then we applied the motion sensors, which were extremely lightweight, and they were just applied to their fingernails. I taught them the first 5 notes on the instrument. Then we did a 17-minute lesson, kind of in the spirit of a beginning band lesson or just a beginning woodwind lesson. It involved using some of the pages of the Essential Elements method book, and then supplemental exercises that were very similar to that, stepwise and types of thirds. After about 17 minutes on the lesson, they performed the test trials, which were what you just saw on the previous task. So the only time I recorded their data was on the test trials, and they played the test trials usually twice, and I'll talk about the different tempos we used in a moment. The wind controller was connected to Logic Pro, and this beautiful output comes from an experienced senior playing at 120 beats per minute, C, D, E, F, G, F, E, D, C, and it's quite even based on the length of each note, and there are no errors. And the color also tells you how hard they're blowing. So there's a little bit of difference here between the orange and the blue, but their breath pressure was pretty steady. For comparison, here's a novice on their very first day at 90 beats per minute, and we can see C, D, E, F, E, F, E, finally found the E, F, G. Got a little bit better here, only 1 bobble. And then the last time through the pattern, only 1 little mistake. So even within 1 time through the test task, they're already increasing their accuracy. So my first research question was, how does tempo affect evenness in playing? And first we're looking at the stepwise pattern. Y-axis is coefficient of variation. This actually shouldn't be there, the duration in seconds. So it's coefficient of variation. The lower the bar, the more evenly somebody played. And we're focused on the blue bars because these are the novices. So at 90, we can see where their evenness was. At 120, they were more even. And then at 180, they didn't actually play that on the first day. That was too fast. On day 2, they were actually less even at 90. They got a little bit better at 120, but still weren't ready for 180. And then we can see the trend for day 3, better at 90, not so good at 120. They were ready for 180, and then day 4. This is the average of 4 participants who are novices coming in for 4 days and playing these tasks. And across 4 days, there's really not a strong trend of them getting better with their evenness yet. This graph includes all of their notes, their correct notes and their incorrect notes. So what I did next was I subtracted out the wrong notes, and in this graph, you're just looking at the correct notes. When we look at just the correct notes, there's a little bit of improvement overall at 90, going from day 1 to day 4. And actually at 180, they got a little less consistent. So now we're looking at thirds, and I've kept the y-axis the same. So your immediate thought should be, wow, those bars are a lot higher. And they are. They were much less even playing the thirds when you include all the pitches. As you might expect, there's going to be more errors, so that's introducing a lot more unevenness as well. So at 90, day 1, day 2, day 3, day 4 started to get better. 120, they weren't ready for 120, playing thirds on day 1, and then day 2, day 3, day 4. Second question, how do pitch errors evolve across days? And what I did is I went through and I categorized all the wrong notes. So possibilities were they just moved their pinky when they shouldn't have moved their pinky. A passing tone would be if they played a D between the C and the E. Multi-finger meant there was more than one finger involved in an error. Repeated pitch would be tonguing or just re-articulating a note. And a neighbor tone would be kind of a bobble where, say, you go from E, F, E, when you're just supposed to land on E. We'll focus on the red arrows. So the novices on day 1 had some passing tone errors, quite a lot of multi-finger errors, a little bit of neighbor tone, a little bit of repeated pitch, a little bit of pinky, and they kind of had a little bit of everything going on day 1. On day 2, at 90, a little bit more on the passing tones. On day 3 at 90, much more on the passing tones, but fewer multi-finger errors. And then day 4 kind of had an even amount almost of those multi-finger and passing tone errors. Next question was, do novices make more errors when they lift their fingers up or when they put their fingers down? For comparison, I've provided the experienced players, and blue bars for everybody means an error when they lifted their fingers up. Orangish, yellowish bars mean when they put their fingers down. So experienced people didn't make a lot of errors. They were really tiny blip-like errors, but they did make more of those lifting their fingers up. And when we look at the novices, it's pretty clear they made a lot more errors when they lift their fingers up than when they put their fingers down. The other trend we see is that they did make fewer errors as they progressed, except when we get to tempo 180. And I only put in for the thirds because for the stepwise, there wasn't really enough errors to make that terribly interesting. Another way to look at this was to look at the ratio of errors from up to down. So at 90, generally there's a trend that they made more errors when lifting fingers up. And at 120 and at 180, there's really not a trend there. Question 4 was, how does finger velocity evolve by tempo and day? So first we're looking at experienced for comparison, and we're looking at millimeters moved per second. Blue is still up, orange is just putting down. And this is telling us at 90 beats per minute, they move their first finger up at about the same speed as when they put it down. And at 120, lifting up is blue, putting down, they move it a little faster. At 180, they actually lift it up faster and put it down slower. So if you think through, I did 90, 120, 180, and we have 4 fingers, you could be looking at a lot of graphs. So we're not going to look at all the graphs. We're going to focus on novices with their first finger lifting up, putting down. Not a whole lot of trends going on here. It's a little bit clearer at 180 that they're putting that first finger down faster than lifting it up. Second finger would be their middle finger. So at 90, not a whole lot of consistency. But at 120 and 180, they do seem to be putting it down more quickly than lifting it up. And then third finger, not a whole lot of differences going on at 90. At 120, you start to see some of the pattern you see at 180, and then at 180, generally putting that finger down faster than lifting it up. Last question, this is really just at an exploratory level because I'm not equipped to fully analyze all the motion capture data. I sought out many people to help me, and I just wasn't a good time to get a collaborative analysis going. So what you're looking at are one participant across 8 days of learning. And these are the fingers that we're interested in. This would be F, E, D, C, or first, second, third, fourth finger. And they are playing the scale pattern. And I've tried to rotate the angle of the motion path to be consistent across days, as well as show, how much is what is the path that the finger's moving. So that's their day 1, day 2, day 3, day 4, day 5. And they did the first 4 days during 1 week. Then they came back the following week. So there's 3 days of rest in between day 4 and day 5, just because she came in on Thursday, and then this day was Monday the following week. They did not take any instruments home, so the only playing they did were in the study sessions. Day 6. And then day 7, she was able to practice, but she wasn't able to test that day. And then our last day, day 8. So looking from day 1 to day 8, it does seem like there's starting to be some refinement of the motion path. So highlighting the clearest results and then bringing in some discussion points, novices did play more evenly when they were playing scale passages than when playing thirds. And when they played at a faster tempo, they were actually less even on the steps. But when they played at a faster tempo, they were more even on the thirds. Maybe they were concentrating harder because they knew it was harder. Next discussion point was in previous literature, the couple studies we have with expert clarinetists, it was found that more tactile information was related to more even playing. So when they are bringing their finger down to touch and when they're first lifting it up, if there was more velocity there or acceleration there, they were more even. So here I found there were more mistakes made on the lift up, which it still does have some tactile information when you're lifting away, but not quite as much. So this might represent some consistency between what an expert does and what the novice is doing right from the beginning of learning. For expert clarinetists, their evenness did decrease as tempo increased. And I did find some trends when they played at 180, their evenness was less even. For kinds of errors, and for me, the biggest application of this is pedagogically knowing that on the first day, a lot of fingers were involved in making errors. But as they went through their practice, most of the errors involved only one finger, and they were more likely to happen when lifting up. And at 180, their error patterns were different than 90 and 120. Since I was in a study session and I'm kind of trying to maximize data collection, it may be that they were playing at 180 before they might have in a traditional instructional setting. So perhaps I pushed them to 180 too soon. That would be something that could be explored in a more longitudinal study. So I would like to thank my university for supporting my research. And this data was collected at Western Ontario University when I was visiting Jessica Grand's lab. And Alex Damos also provided some insight for me in my initial analysis of this data. So thank you for your attention, whatever time of the day it is for you. And if you have any questions or comments, I would be happy to address them.
Great, thank you very much, Laura. That was very interesting. And I'm a saxophonist, so
Oh.
I have a lot of questions, but I don't want to monopolize the question time. But I'm looking to see at my chat. Anyone can raise their hand if they want to ask a live question. If you want to ask something through the chat, I will try to see those. But let me just, I guess, failing to see a hand, I can ask a couple of questions, and I'm just wondering why you used a MIDI controller instead of like a real soprano saxophone or a clarinet.
Part of it was for sound production, that it is easier. With the wind controller I was using, it does have a synthetic reed and it does have a mouthpiece, but it still is easier to get a consistent sound than with a traditional reed and a traditional mouthpiece. And then the rest of that was because I wanted that digital accuracy in terms of the timing, and that it was three years ago when I started collecting the data. I felt like that direct connection of a MIDI instrument to Logic Pro would give me just better resolution than perhaps using a soprano saxophone and recording it into Logic Pro or something like that. I was really trying to maximize accuracy on timing.
Yeah, I'm wondering from the mocap data, do you think you could have distinguished when a finger was up and when a finger was down?
I do think I can distinguish that in there. Well, I personally cannot. I think the information is there, but I am not able to analyze it that way.
Okay, I see a hand up from Matthias.
Hello, thanks a lot for the talk. I first was wondering what level are the experts? Are they student experts or professional experts?
So in the previous lit that I was citing, they were experts, like from Carolyn Palmer's and studies. But the people in my study were experienced, is what I called them, because they were college undergraduate music majors, and then people in the amateur ensemble, the adult amateur ensemble, who were not professionals but had been music teachers and playing for 50 years. But again, they were not professionals. So they're accomplished, but not a professional.
Okay, well, because I assume there's really a difference to professionals practicing really every day, a lot of hours for perfection. And there is one thing I would be interested if you increase in smaller steps by 10 BPM from maybe 120 to 200, because when does the chunking comes into the place? When do you learn to play different by practice chunking? So it's sometimes more difficult to play slower, very exact, than to play faster. So if you have 10 BPM steps, it would be seen if it's get worse if you play very slow, or if you get a changing variation to playing chunked notes in very fast tempi.
Yeah, I think that's an excellent point. My intention was for them to memorize the pattern to hopefully lead towards some more chunking, and the scale one they could, but the third one, they were still really reading those notes. Those patterns were not that well chunked at that point, and I can see how that would be interesting to see. Yeah, can we even tell when it starts to chunk? Is there a shift in their evenness? So thank you for that suggestion.
There was one question in the chat from Sarah DeMario. Said, very interesting, thank you. Could you please clarify how many participants by expertise group took part in the study?
There were 4 experienced, and they came from saxophone and clarinet and flute backgrounds. And then the novices, there were
No,
8 of
I'm
them.
just gonna listen while I get dressed.
There were 8 novices.
Halloumi. That's halloumi.
Just,
This
Brenda, can you mute, please? I had another, I don't see any more questions, but I had a question that, the way the keys work on a MIDI wind controller is quite different than on a, it's less tactile feedback on a MIDI controller than there is on a real instrument. And there's also differences, potentially whether your fingers over a key versus over an open hole, like in a clarinet. So I'm just wondering if you have any comments about those aspects.
Yeah, I did make a choice to use the MIDI wind controller because I really wanted that timing accuracy, but there are certainly compromises that it's not the same as a clarinet. Potentially, there might be less tactile feedback on that, like on the third, on the C key of a clarinet, say, right, where you don't have any ring to put your finger on. Maybe there's even more feedback on the low pinky key on the clarinet because you have to press even harder to get those low pinky keys down. So that potentially, those differences could cause differences by individual finger in terms of accuracy, or really in terms of evenness, I think. And that's something that could be explored on true acoustic instruments.
I think the one complication with a real instrument is reflections. If you try to use a mocap system, you often have problems with reflections from metallic parts of the instrument, but you can start covering it up with tape.
Right.
Are there any other questions? I had a quick question as well. I wrote down a whole bunch of questions, but we won't get to them all. But when you calculate the coefficient of variation, is it normalized by the length of the note? Because the higher tempo results seem to be a bit better, at least initially, than the lower tempo ones. But at that higher tempo, each of the note lengths are a lot shorter.
It is standard deviation divided by IOI. My understanding is that it has normalized them.
Yeah, I'm not familiar with what that calculation would be, so I didn't know.
It's in relation to the duration of it is in relation to the duration of each individual trial. So it's not directly comparing the length of 180 to 90. It's comparing the variability within tempo 180 and then the variability within tempo 90.
Okay. Okay, we need to stop now. So thank you very much, Laura. That was a really interesting study. And we're going to move on to the second presentation, which is a recording. So the presentation is the effect of expiratory muscle strength training on the performance of trumpet players. The authors are Alexandra Türk-Espitalier and Matthias Birch from the University of Music and Performing Arts in Vienna, and Isabel Cosset from the Schulich School of Music. And Bernice is going to start the recording for us. Oh, before we do that, sorry. Matthias, are you prepared to answer questions? Oh, I see
Alexandra is here, yeah.
Okay, great.
Well, actually, I am here, but I submitted the video because I sometimes do have internet issues. So I thought the video would be safer, so I can do it as you wish. I mean, I can do a live presentation, but the video, of course, is safe. As you wish.
I will run it. I will share my screen and run the video, okay?
Okay, yeah.
All right, let me do that now.
Hello, dear ladies and gentlemen, dear colleagues, dear friends. I am Alexandra Türk-Espitalier from the University of Music.
Can you all hear the video?
I could hear it, but now it's stopped. Did you
Yes,
stop
yes.
it? Okay.
Yes, I'll resume it in a second. Okay.
Okay, great.
And Performing Arts Vienna, and today I welcome you on my lecture on trumpet players. So I will start right away and open my screen for you. Today I will speak about the study we conducted here at MDW, and it's about the effect that expiratory muscle strength training has on the performance of trumpet players. So let's start with some basics first. Any wind instrument needs a minimum necessary pressure in order to produce a tone. Blowing pressure and rate of airflow vary notably among the different wind instruments and depend on the construction of the respective instrument. The trumpet is a low airflow, high pressure instrument and requires quite high intrapleural and intraoral pressures, especially in the high register and when playing loud. Playing in the high register is quite an important topic for trumpet players. Players take great effort in not only improving their overall playing technique, but also to learn an effective technique for the high register. Without this effective So let's take a look at two very well-known excerpts from trumpet literature. Here you see two examples that you probably all know: Alpensymphonie by Richard Strauss and Haydn's Trumpet Concerto. In the Alpensymphonie, you see that the highest note is a sounding D6. In the Trumpet Concerto by Haydn, the highest note is a sounding D flat 6. So that's actually quite high. And these difficult notes on the high end have to be produced and reproduced with consistency and stability in concerts and auditions. That means that the players have to be able to generate the necessary pressures, not only in a relaxed situation, but under difficult circumstances as well. So let's take a closer look at these pressures at the following slides. Here you can see the intraoral playing pressures among the different wind instruments. You will notice that the medium pressure is not spectacularly high on the trumpet. So just some comparison with other tasks: whistling would be 7 centimeter water, forced speaking 14 centimeter, blowing out a candle from a distance of 50 centimeters is 27 centimeters water, and blowing up a balloon is like 81 centimeter water. So the trumpet with 18 to 57 centimeter water is not spectacularly high. But if you measure maximum pressure, you will see that the trumpet is clearly the instrument with the highest intraoral pressure. There's actually quite a difference in value between the different authors. You can see that here, going from 171 up to 258. And this is because of variable conditions during playing. So actually, unfortunately, no reliable values can be presented. But despite this inconsistency, researchers agree on the increase of flow and pressure with rising dynamics and pitch. Except that, I have to say, for the clarinet, where pressure rises in the low register compared to higher notes. Now, how is the necessary pressure produced? Physically, it is always a combination of embouchure, control of airstream, and expiratory muscle strength. There's also a mental component, which I will come to later. For now, we'll stick to the physical aspects. And what we were interested in particular in this study was expiratory muscle strength. Expiratory muscle strength because the pressures have to be generated while exhaling. So we asked ourselves if there is any additional training, that means additional to practicing and exercises from trumpet lessons, that trumpet players could do to improve reliability and stability in the high range. First, we looked at respiratory training and the devices that are commonly used among brass players. Many brass players use breathing training devices in order to enhance their physical strength, visualize airflow, and enlarge their breathing capacities. Several types of respiratory training devices originally developed for patients with respiratory diseases that are also used in brass pedagogy are depicted here, and you might recognize some of them. A problem with training among brass players, however, is that intensity and frequency of training often remains unstructured and follows tradition and the principle of trial and error. So we decided to conduct a pre-post intervention study with trumpet players, doing an additional expiratory muscle strength training and test whether this training has any influence on their playing, especially in the high range. 24 male trumpet players from Vienna took part in the study and did a 5-week strength training of their expiratory muscles. Here, you can see an overview of the study design, depicting the two groups and the times of measurements. So here you can see the control group, here the intervention group, and we had initial measures and final measures that were done at the beginning of the 5 weeks intervention and at the end. And the intervention group also had weekly measures of their maximum expiratory pressure to adjust the training load. The measurements were divided into performance parameters and physiological parameters, as you can see here. So length of tone, pitch, and dynamics was considered performance, and muscle activity, perceived exertion, and the specific expiratory muscle strength measured via the MEP, the maximum expiratory pressure. These measures were considered the physiological parameters. Assessment tools were a 7-channel surface EMG, sound recording, the Borg scale from 6 to 20, and the spirometer. The muscles we measured were the expiratory muscles of the abdomen and the auxiliary respiratory muscles of the shoulder girdle. So you can see them here on the left for the abdomen, the rectus abdominis, the two obliques, the external and internal oblique, and the intercostalis, and at the shoulder girdle, pectoralis major, the trapezius, and the SEM, sternocleidomastoideus. All participants had to play standardized tasks, which you can see here. The playing tasks basically were long, loud, and high notes. So we had a long sustained G, then a G major scale where the participants should play as high up as possible. Then the third task was that they had to play loud notes, long loud notes. So basically it was G major triad, but the notes were separate. And the last task was a transcription or transposed version of the theme of the second movement of the Haydn concerto, to make it a little bit more difficult. The beauty of tone was not measured. It was important whether the participants were able to still play the note or not, but it was not important whether it sounded beautiful.
All participants played the tasks on their own trumpet and mouthpiece, because in so-called high-end playing tasks, it is important that the players know the instrument. And without feeling comfortable and being used to the mouthpiece and to the feeling of the rim, it is basically impossible to play high-end tasks at a professional level. The Borg scale was filled out directly after finishing the playing tasks, and the maximum expiratory pressure was measured after a short break after the playing tasks. And here you can see a participant in action. And here you can see another participant doing the MEP measures. All these measures were done for both groups, intervention and control group. That means at the beginning and at the end of the 5 weeks intervention, although the control group did no training during those 5 weeks. The intervention group did their strength training with the EMST 150. It's a pressure threshold device that you can see here on the right. Every participant got his own device to train at home. Training intensity and frequency was set according to other studies that used this device. And to ensure adherence, the participants filled out a daily training and practice diary. The training load with the EMST 150 was adjusted weekly to 60% of the latest MEP. After the 5 weeks of training, all measurements were repeated. And the results were actually quite interesting. So let's take a look at them. Here you see the maximum expiratory pressure, MEP. And you can see it increased a significant 13% in the intervention group. Here on the left, A is the control group. B, here on the right, is the intervention group. Red is pre-intervention, blue is post-intervention. Both groups started with a mean MEP of 212 centimeter water, respectively 213, and the intervention group finished with a mean MEP of 241. So you can see that increase clearly here on the right. The length of the G4 was measured in seconds, and there was no significant difference between the groups and also pre-post intervention. The same with the highest possible tone. The tones, or the pitch, was converted into MIDI. So MIDI 68 is a sounding E6, and that stayed exactly the same in the intervention group, pre and post training. The control group even decreased half a tone to a D sharp. Dynamics also didn't change significantly. You can see the mean volume in decibel, and the mean value dropped only 1 decibel in both groups, which is extremely little, but there was clearly no improvement that they could play louder. The rate of perceived exertion on the 6 to 20 Borg scale stayed the same in both groups. It was like the other measures. It could have been, that's what we hypothesized, that the intervention group found it subjectively easier to play the tasks after the training, but that was obviously not the case. Let's continue with the data of the surface EMG. Here you can see a screenshot of the raw data and the measurement setup. That's how it looked like. Now, this data of the surface EMG was analyzed at 3 different places in the playing tasks. So muscle activity at the G during the scale was expected to be rather light. The fortissimo B and the high C sharp were expected to show high muscle activity. It was hypothesized that there could be a difference in muscle activity because the B is an isolated note, whereas the C sharp is embedded into a legato phrase. Generally, results showed the highest muscle activity during the isolated loud B. This occurred in both groups, pre- and post-intervention alike. Generally, we could say that muscle activity increased with pitch and loudness, but no significant difference was found between groups and also not before and after the intervention. As an example, you can here see a table with the percentage of maximal voluntary contraction of the external oblique. So we have pre and post of the G4, the B5, and the C#6 here. And we have control group A and B. And you can see that between groups and also pre and post, there was really no significant difference. Now, if I sum this up, we can say that we found a significant increase of 13% of maximum expiratory pressure in the intervention group. This rise of MEP after the training is in general agreement with previous studies. Because if general principles of strength training, such as specificity, overload, progression, and reversibility are observed, an increase of strength after a specific training is predictable to a certain extent. All other outcomes, including performance outcomes, did not change significantly, which means that there somehow seems to be no transfer to performance of the gained higher MEP, which is very interesting. So, of course, we ask ourselves what could be the reason for that. First of all, a plateau could be responsible for the missing transfer. Both MEP value and playing level were already very high in all participants. Compared to a non-trumpet playing population of the same age, the participants in this study started already at 150% of the average MEP. The same with the playing level. All players were professionals and therefore already very good. Furthermore, strength of the expiratory muscles is only one component of tone production on the trumpet. In an earlier study, my colleague Matthias Berg found 58 different variables responsible for tone production. These include not only physical parameters, but also mental ones, such as imagination, concentration, and motivation. So it is possible that an improvement in just one parameter, such as the MEP, is not enough to lead to a change in performance. Then we also have the form of the day. That can vary tremendously and is extremely difficult, if not impossible, to measure or to predict. The results of this study are similar to those of previous studies investigating the effect of EMST on performance. The populations of these studies can be roughly categorized into 5 groups. That's patients with neurodegenerative diseases, patients with chronic obstructive pulmonary diseases, COPD, persons with voice disorders, athletes, and wind instrument musicians. Only in patients with neurodegenerative diseases, a significant change in performance outcomes was repeatedly reported. In subjects with COPD and voice disorders, results were inconsistent. In athletes and musicians, a transfer of increased MEP to performance could not be found so far. So all 4 participants showed a higher MEP and therefore increased strength in their expiratory muscles after the training. They were not able to use this strength gain to enhance their playing. So the effect of EMST on playing performance do not seem to surpass the effect of practicing alone. Therefore, recommendations for EMST have to be seen critical, at least for a population of professional male trumpet players with a well-trained respiratory system. For other populations, such as women or adolescents, who naturally cannot or not yet produce very high MEP values, EMST could be beneficial and an interesting addition to instrumental practice. Furthermore, amateurs with a lower playing level as professionals might benefit from EMST. However, this has to be investigated in the future. So, I thank you for watching this presentation, and I'm now here to answer any question that might have come up.
Great. Thank you very much, Alexandra. I very much enjoyed that as a wind player, but not a brass player. And I do have questions myself, but I'll open it up to our audience first. If I see some hands, I don't see anything in the chat. I had one question about how these pressures were measured, like the intraoral pressure and the pressures that you use to assess dynamic level.
Well, we measured it with the spirometer, one that you saw in the video, where they were just blowing as hard as possible into the device, and the device has a preset resistance. So you can then measure the force in centimeter water that they can that the players or the participants can produce. And this maximum expiratory pressure is it's the reference value for the pressure that can actually build up. We did not measure like intraoral pressure with the means of like putting that small like the small tube on the side on the in the mouth while they were playing. We did not do that during playing.
But for the assessment of dynamic, because you said they didn't increase their dynamic level, so that was through some sort of microphone?
Yeah, dynamics was measured just very simple with a microphone. So the distance was set. I mean, they had a set place. Also, the distance from the bell of the trumpet to the microphone, it was 50 centimeters. So that was measured. They should stand as still, of course, as possible, not like move the trumpet around. And we had, like in our room, I mean, we could not measure it like in a, we did measure it in the same room though, but not like in a special chamber, but still it was the same acoustical situation for everyone, but it was just normal microphone, yes. So it was decibel in that room with that preset distance.
Thank you. I had another question. I guess the participants weren't given any training about body posture as well, like things that they could improve about their body posture or their chest configuration. So all you were doing is just giving them this device, and
we just gave them this thingy, and so actually they filled out the practice diary also. So we made sure that they didn't do anything parallel to that, because sometimes they're so motivated. Well, so they get this thing to train with at home, and then they sometimes think, okay, maybe I do something additional. So we made sure that they did not do anything additional, what they just didn't do anyway. So just their normal practicing and this. Mm-hmm.
See a question from Laura.
Mm-hmm.
So I'm thinking about their new or enhanced capability with their breathing and applying that to an existing skill, which perhaps is difficult. So maybe if there was a new skill that they could use it with, but then I'm thinking, well, what is a new skill when you're already at that level? Could it be that they just need more weeks to integrate their new capability into their existing motor skills? 5 weeks seems like a pretty long treatment. Did any of them comment on anecdotally on anything about maybe using it longer or something like that?
Well, they did comment, because that was very interesting. They all liked it very much. They actually really had fun with it, and they all thought, like during the 5 weeks process, they all thought that they actually could play higher, and they were really anticipating like the final measurement, like, oh yeah, it will probably be better. And then they were like kind of disappointed when that was not the case, and they had to face the reality. So there were several who said, yeah, well, they like it and they're going to use it after the study. But actually, I did not check whether they did it or not. Yeah.
Thank you.
Mm-hmm.
The reason I asked about the training and the posture, because I went to study in Bordeaux for a year with Jean-Marie Landex, and he had this study where you would play scales as fast as you can for the full range of your instrument over and over and over again until you ran out of breath. And so you were supposed to incrementally be increasing the tempo as you could, but you had to play it cleanly. And I definitely improved over 4 or 5 months. But he also talked about my posture and a way of really increasing my lung capacity. So in the beginning, I could barely do 2 full rounds of the range of my saxophone. And by the end, I could do 3.5 or so. I think, of course, my tempo increased too, but, and that covers the whole range. So that would also work on the high notes.
Yes, but I suppose, I mean, this is just an opinion now, not a fact, but that would probably fall into what Matthias found out, the different variables, the different factors in producing the tone, because when you practice like scales over the whole range, just as an example, for 3 weeks, you get better like in any aspect, also like in being more efficient with the embouchure, in structuring probably the tempo better over the length of your breath, and just these many different variables. So it could be that if they did that, they also increased the height, yeah. But this is something we can only, I don't know, speculate now. Yeah.
I just a second to stress again the important fact that they all are above 18 and very strong lung men. So it would be very, very interesting just to check if you are too young or not able to perform 120 centimeters. Then it would be interesting to use that tool to increase your lung capability and then to increase your range of playing. So if you have an entrance test for this kind of training, you are not able to have this lung pressure, then it would be really a good study again.
Thank you very much. And I just noticed we're pretty much out of time. So thank you very much to the presenters. And we're going to move on to the last paper of this session, which is a comparative study of respiratory kinematics during phonation of female and male singers using dynamic magnetic resonance imaging. And there's quite a few authors, but the presenter is Louisa Traser, and she is with us, and this will be
Yes.
in-person sort of presentation, correct?
Yeah, thanks a lot for the kind introduction. I hope everybody can hear me well, and I will start the presentation in a second. I just have to share the screen and then give the tone for the video. So, and then I have to start here. Perfect. Yeah, very happy to be here, and for the next 20 minutes, I want to speak about sex-related differences of voice production, and I'm very happy to present a study based on data from dynamic magnetic resonance imaging, where we compare respiratory kinematics in male and female singers. So let's first have a look on what we know about differences in voice production between males and females. So voice production is regulated by three main parameters: the larynx and the vocal fold vibration, the vocal tract, and the breathing apparatus. So let's first have a look on the larynx. And I brought you a video of a professional singers. Have a look inside, and you see here the epiglottis and the arytenoids, and you will see the vocal fold vibration. And I will also play you example of a female professional singers, and you can see how the vocal folds are vibrating for the sustained note. And with the first glance, you can see that there are length differences in male and female vocal folds. But what's even more interesting is how the vibratory mechanisms work in singing voice production. And when we take Western classically trained singers, we find that during their voice range profile used for their stage voice, female singers use more a kind of a middle register or an M2 mode, which means that the main vibratory parameter is the epithelium and not the whole vocal folds. And this is in difference to male singers who spend a lot of their stage part of voice in their model register, where the whole vocal folds are vibrating. And we find therefore differences also in a measure that is called electroglottography. So here we apply very small currents on the larynx, and we can see how the currents differentiate during phonation. And we can see that male singers have a very constant quotient and not a great relation to the pitch. This is a difference to female singers, where we see a clear relation of the contact quotient to the pitch. So that are distinct physiological, anatomical differences between males and females that were described in the past, and also during speech production, males use males use a lower open quotient or a higher closed quotient. So that would be the differences in the vocal fold vibration. But what about the vocal tract? So the voice source now is filtered by the vocal tract, and I brought you some MRI images here that where we modulated the vocal tract from 3D MRI, and we can see how the vocal tract changes the voice source, and also the other way around, we have interaction between these two systems. So what about differences in males and females? So on average, the male vocal tract is longer, so that brings us to a difference in where are the frequency maximums of our resonance frequencies, the formants, and the first two formants are related to the vowel we are producing. So we find difference here. But what is even more interesting for singing voice production is when we see how a professional trained singer gets a loud or a projective voice. And I brought you a video of a male singer singing pianissimo and also fortissimo. And it gets clearer when you look at the at what I brought you here. So male singers, they reduce the area just above the vocal folds, which we call the epipharyngeal tube. And this is what we know as for creating the singer's formant. And this is a principle where we focus energy in an area where our ear is very sensitive. So that makes sense for a classically trained singer to use that kind of loudness production to be audible above an orchestra. And this is just a very recent study of our colleagues in Berlin, and they found also this principle in their male singers. So they found a correlation of sound pressure level. When it was increasing, the singers were narrowing their epilaryngeal tube. And it's very interesting that that was not the case for their soprano singers, where they describe a constant epilaryngeal tube. And this could be related to the fact that, that female singers, especially the soprano singers, may have another concept for creating loudness in their sound, and they probably are adapting the vocal tract resonances to the fundamental frequency, which we call tuning. So as you see, we know already that there are some distinct differences in singing voice production between males and females, but what about phonatory breathing? So there are former studies. They used magnetometry, which is a technique that measures anterior postural diameters. And they studied kinematics, but did not find any difference here. But in a survey based on 55 professional singers, Scott McCoy found that female singers concentrated their breath effort lower in the body than did male singers. So we found that a very interesting perspective to have a closer look using a new technique, dynamic magnetic resonance imaging, also for the respiratory system. So we have 3 to 4 frames per second that we acquire. We have a simultaneous electroglottographic measurements. The subjects are placed in supine position like that. And we ask them to sustain maximum phonation times at different pitches and at different loudness condition. So let's have a first example of a female singer. You won't have the audio, just see the movement kinematics. You see her inspiration and the phonation. So that is a bit time lapse to make it more quick. And now you can have a comparison to an example of a male singer. See him inspirating and phonating. Now let's look at both again simultaneously. And you may realize that the basic movement principles, they are the same, but they are distinct differences that we want to have a closer look now. And to do this with a scientific approach, we have chosen different measurements that we acquired in every image frame. And from that, we have raw data movement curves. And of course, every singer has her or his own dimensions of the system. So to compare kinematics, we do a normalization, and then we can now here look at 6 different female singers and 6 male singers in this study. And first we have the impression that both have very similar movement velocities, which are characterized by this elliptic shape. And this elliptic shape comes from the following principle. So in the beginning of the sustained phonation, the singers kept the anterior diaphragm and the rib cage in a more inspirated position, so it moved slower, and the other way around, the back part of the diaphragm elevated first. And then in the end of the phonation, this movement principle changed to the opposite, and then the thorax is lowered first and the diaphragm elevates slower. And we found both very similar in male and female singers. And you can also extract the gradient from this and do mathematical analysis, and this was statistically not different. But then in the next step, we wanted to have a closer look to the individual differences of these kinematics. So therefore, we normalized the data to the maximum inspiration and the maximum expiration, so their maximum possible movement of their respiratory system. And when you do that way, you get a bit of different view on these curves, and you can see a distinct difference already here. So our female singers, they used about 65 to 75% of their possible inspiratory capacity of the thorax. And this was the main difference to the male singers because they used about 85% of their possible movement capacity of the thorax. And you can see a more differentiated look when you look at the movement range. So the movement during phonation compared to the movement range during sole respiration. And when we set these two measures in relation, then compare between male and female, we find also a statistically significant difference. And here males use 20% more thoracic movement compared to the females. And there was a tendency for the females to use more diaphragmatic activity. But of course, don't forget, it's just 12 singers. So statistic is, of course, rather critical here. But that would be in good agreement, which was Scott McCoy told us from his survey. So let's discuss these findings a bit with a view to the interactions between the three systems that we are looking here. So when you activate the diaphragm for inspiration, then something is activated that we call the tracheal pull. So the diaphragm pulls the larynx downwards when it's not by muscular force hold in position. So that is of course the pre-requirement for that. But if the larynx would be free in its movement, it would be lower and the vocal tract would be longer when we activate the tracheal pull with the diaphragm. And it's really interesting, Johann Sundberg described this relationship already in the 80s, that the diaphragm activity is related to the activity of the cricothyroid muscle. And the cricothyroid muscle is a muscle for the tension of the vocal folds, but also for a little abduction. And let's think back of the introduction where we found that our female singers have a vibratory pattern that is more based on a higher open quotient. And when we have a stronger tracheal pull by using the diaphragm for our respiratory patterns, you would probably get a larger variation of the length of the vocal tract. And maybe that is something that female singers can do because it's more acceptable in the higher frequency range. Because when I phonate at 1000 hertz, then I would have my spectrals at 2000, 3000, and so on. So where the formants lie in the resonance spectrum is less audible, and therefore changes in laryngeal position would be less audible in female singers. And when we look at what would be related to a smaller reduced tracheal pull by using more ribcage activity, we could think that this might be related to less CT muscle activation, and think of our male subject with a higher contact quotient. And also we could think of that in that way, it's maybe easier to maintain a constant laryngeal position. And this is something that is especially important for the lower frequency range, because here we have a lot of harmonic partials, and changes in the laryngeal position would be directly audible also in the sound. So that were the thinking that we had on this data. But of course, the question is this really about the sex of the subject? So it could also, of course, be a fact of other factors like the body height. The male singers were taller in our study, and with only 12 subjects, no subgroup analysis was possible here. And another factor could also be the weight. So there are studies that postulated that with an increased body weight, we have another strategy where the breast support also lays lower in the body. And what about non-classical singing? We are now doing a study on trained singers with a still voice training, and I found it very interesting to see here that when a female singers changed her voice production from the classically sound, the opera, to what they call belting, which is a really strong pop sound. And then belting is a sound that is produced by shortening of the vocal tract and by a vibratory pattern that is where the whole vocal fold is involved in the vibration and has a strong closed quotient. So when we compare the data between opera and belting, it's interesting to see that the female singers change her breathing patterns and increase her thorax movement for belting. I have a little video to show you that here. So that was the belting example. And that is the opera example. So I find this correlation quite interesting, but of course it's only 12 singers. So yeah, we can only see this tendency here, and we cannot really answer questions whether this is related to anatomical, physiological differences related to sex or other constitutional factors. But we see a lot of respiratory kinematic differences. And I think what's important for me to give you home is that I think that as a voice teacher, it's important that I'm open for different respiratory approaches, and not because I found a way that's good for me does not mean that it's the same for my pupil. And I think that's one thing that we can take from the data. So that was my presentation, and I'm very happy to answer your questions.
Thank you very much, Louisa. It was very interesting and outside my domain. Is definitely you don't want to hear me sing.
Oh, everything can be learned.
So do we have some questions? We definitely have a little bit of time. I had a question, just a practical issue. You know, people had to be strapped into this machine and inserted into a tube. Did anyone complain about the conditions under which they were trying to sing?
Yes, of course. One factor that I didn't also mention is the supine position, and I think that is also a very important factor for singing voice production. So yes, also the MRI machine is very loud. You don't get a good feedback, so therefore, yeah, it's really interesting to see these videos and to see these motions, but I think you really have to keep in mind that the surrounding is very special for the singer. That's true.
The first ones you showed were more, the side angle ones were more X-ray fluoroscopic as opposed to MRI.
Sorry?
You had some cross-sectional videos you showed in the beginning, and I thought maybe those were X-ray fluoroscopic as opposed to MRI.
No, they were all MRI.
All MRI. Okay.
The first one of the glottis are just stroboscopies. That was to give because I thought when we're not all ENT doctors here, it's good to have a look on what's happening there. Mm-hmm.
Kevin has his hand up.
Yeah, thanks. Very, very interesting paper. I noticed in the protocol that you had them connected to an electroglottograph, but you didn't report on any data from the electroglottograph. So I was just curious, what was the purpose of that? And if you did collect data on that, did it correlate with, in terms of the contact quotient and the breathing? Because I would think that that's the valve, right? So that's going to have an impact on how people are breathing.
Yeah, thanks. That's a really good comment. And yeah, for the sake of time, I couldn't go to all the details. But yeah, we do collect the electrograph because when you measure respiratory kinematics in singers, you really want to know what's happening at the glottal area. So that was the main purpose, to see that they were not changing their vibratory mechanisms during the phonation. But still, we also analyzed this data and we could also find these differences on the contact corrosion that I reported in the beginning. But of course, the data during MRI is a bit so the MRI makes a really loud sound also into the EGG data. So therefore, it's not so good for really close evaluation. I would also suppose that during phonation, normally you find an increase in contact corrosion. So the contact corrosion sometimes correlates to the lung volume, but this is a bit less the fact when you have professional singers, because they are really used to use a very high part of their lung volume. And yeah, so for that, we did not go into detail of the EGG, but we analyzed the general contact corrosion and and we checked that they did not change the vibratory mechanism during the sustained phonation.
Can I ask just another a sort of follow-up question to that? Because I've done some research with the electrocardiogram. One of the pain in the butts with it is keeping those darn sensors in a stable position.
Yeah.
With the moving in and out, was that an issue, or did you put them on really, really, really tight?
Yeah, that is an issue also because what I said, especially females, they use a variable larynx
position. Yeah, and it goes in and out.
Exactly. yeah. Okay, that's okay. Sorry. So we have for the MRI machine, we had to adapt the EGG. There's a paper on that. And we are using very large electrodes, which are not magnetic. So that's the pre-requirement. But still, for the really high pitch, especially in the females, there we always have the fold that the EGG signal then goes sinusoidal. When you're a bit out of the range where you want to measure, the EGG signal goes sinusoidal, and that makes. And a sinusoidal wave has a contact corrosion or a deviation of 1. So no, I don't know the English word. I'm sorry, but so that makes that complicates the evaluation of the contact corrosion a lot. But maybe you know the work of Sten Tenström, and he has this very, very good phonation program. And using this at the base for the EGG evaluation helps a lot. So
all right, well, I do have more questions about that, but I'll follow up with an email to you. Thank you.
Okay.
Thank you. I see Isabel has her hand up.
Yes, I was. Hi, thank you very much. That was very interesting. Yes, I think that I was wondering if you had measured the changes of, chest wall and abdomen standing versus lying in those singers, because of course I'm pretty sure that it changes the gravity and the the functionality of the diaphragm will change when lying and everything. So I was curious to know if you had checked standing, if you could see at least externally some differences.
Actually, I just have a paper under revision on that, so hopefully it's not too long that it's free. So we did a study with a tiltable MRI. So we are really lucky in Freiburg to have a tiltable MRI. And this is, of course, very important for us because we do a lot of studies with MRI and we have a strong effect of the position. And in this study, we found that when you're lying, you use more ribcage activity than compared to upright. So yes, it's changing, and therefore it is limited. But of course, all singers were lying. So I hope that what we find is still a difference, which we would also find in upright. And we cannot do all the studies upright because this MRI is very slow. So it's just about having an idea of how the principles are working upright and supine. But you cannot do really dynamic studies using that one. So that is a limitation. But we also found this for upright and supine vocal tract MRI, and we find that for the supine situation, the larynx is higher, and this is probably because also the diaphragm is higher and the tracheal pole is lower. So that is quite systematic. And so we did a lot of studies on vocal tract imaging as well, and we find that the movement principles are the same, but they are in another range. So the fold is systematic. So therefore we hope that what we see here is also a systematic fold, but you're absolutely right. So yeah.
I also have a small following question in the sense that is there a way you could look more at the dynamic, in fact, sorry, I switched to French, during that, because, well, I know that the length of the diaphragm, of course, is associated with its strength or its power, let's say. So maybe using those, there are some papers from Aliverti that is talking about the length of the diaphragm and how you can get to know its power and everything. So it would be interesting to know, because I don't know if, yeah, I'm curious to know what is the reason. Okay, it's very interesting.
Yeah.
Thanks.
So what I would really love to do is, I think what you did with the the esophagus EMG, and because that in using MRI we can not say something about. So we can see when something is moving, but I don't know something about the contractile force of
yes,
the...
but you look into there are some papers that are talking about the length of the diaphragm and how it is strong. I mean, its strength, because as related to, I don't remember how it is said. The length,
I think
the length force relationship.
Exactly. That is what was postulated when singers use this belly-in technique. So there's another kind of technique where you inspirate by putting the abdomen inwards, and then you put the intra-abdominal organs upwards, and then the diaphragm is longer. And this says, okay, that makes the contractile force of the diaphragm better. But yeah, I cannot measure contractile force with the MRI, and we have a problem with this belly in the supine position. So that would be a really good study if we would have diaphragm EMG with a esophagus catheter. So if anybody of you has something like that, please come to Freiburg, or I come to you.
Okay, thank you.
There was a couple questions from Anna Niemand. I think the second question was answered, but the first one was asking about activation strategies of the diaphragm in female singers could be a result of different strategies of pelvis muscle activity.
Yeah, that's true, because it's the question is, what do you do with the other? So the internal organs, they are not compressible, so they have to go somewhere. Yeah, so it's always a question, what's happening with the abdomen and with the pelvis floor. And I know a colleague of mine, he's doing MRIs of the abdomen, because you cannot measure both at the same time, because it's the field of view is limited. But he's doing abdominal MRI in singers, and I'm really curious on his results. So they will present it at the PASS conference in Vienna next year. So I think that's an interesting study to wait for.
Great. That brings us to 9:30. So that would be the end of this morning's Stream B Capturing Performance session. So thank you, everyone. Thank you all the presenters and all the audience. And so there's a break now, I think, and then there's another session that's going to start up, or sequence of sessions that start up at 10 o'clock. So thank you very much, everyone, for tuning in. And thank you again to all the presenters. Really enjoyed it.